Let's look through this nice schematic to understand the cascade of nitrogen in unreactive and reactive forms with unintended and intended flow through the system. We'll look at other figures of a similar nature. So here, just to run through, unreactive dinitrogen is basically N2. N2 is very inert in the atmosphere, so unless it gets fixed by lightning and fossil fuel burning or by the microbes in the soil and ocean, it doesn't do much. Forms 78% of the air we breathe. NN, reactive nitrogen, is fixed in the soil by microbes, reacts to form different compounds with various impacts. So in the natural form, obviously it's a symbiotic system for soil microbes, vegetation, soil health, soil nutrient cycles, and so on. Ammonia, used for making fertilizers, can escape into the air as a pollutant. NH4 and NO3, ammonium and nitrate. So ammonium nitrate acts as fertilizer when synthesized in the atmosphere and contributes to particulate matter, which are a health concern, water pollution, which is not good, and of course results in eutrophication. We will see what that is. Basically, when you have excess nutrients, there are excess phytoplankton blooms which are not grazed down by the zooplankton because they don't grow as fast. And then the phytoplankton dies and sinks and is respired by the microbes, which use up all the oxygen and create what are known as hypoxic and anoxic regions in coastal waters and lakes and rivers, which can seriously affect other life forms, right? Nitrous oxide, a greenhouse gas, depletes ozone layer. NOx, measures of NO and NO2, a major air pollutant. NO2, NO3 minus, Nitrate, the form in which nitrogen gets fixed in soil, can pollute water sources, forms ozone, which adds to particulate matter load. So looking at this cartoon here, schematic, obviously for all the transportation and energy production, we are doing fossil fuel combustion at high temperatures, and that produces what is referred to here as unintended nitrogen flows at different stages of the cascade. So the numbers here in metric tons per year, so 40 goes into NOx, what we call NOx, which obviously go into ammonium nitrate in rain and then create acid rain and so on, and end up into nitrate streams, groundwaters, and coastal seas, and then eventually back into through denitrification into dinitrogen. Okay, so I won't go through all of them, but you know that fertilizer manufacture is a massive source. You can see here it's an intended nitrogen flow of 120 metric tons, and we are using it for crop food and animal feed. So there is crop biological nitrogen fixation adding to it, and that is having unintended leaching of nitrite and other reactive nitrogens that eventually make it into streams and groundwaters, coastal waters, and then get denitrified back into N2. Okay. So there are temperature and rainfall effects on all these, especially extreme events and extreme temperatures and so on and so forth. And then there are of course livestock for farming, nitrogen manure being added in reactive nitrogen added in manures in addition to the fertilizers. So there are ammonia running through the system directly and indirectly, and so on and so forth. So obviously there are various steps involving intended nitrogen that we are putting in, and there are unintended nitrogen flows that are running through the system in fixed and unreactive and reactive forms. So the net effect is to then go back to the food and agricultural system and try to see what are the environmental impacts. So we are looking here at greenhouse gases, land use, freshwater use, eutrophication, and biodiversity. So food industry, 13.7 billion tons of CO2 equivalent, 26% of the global emissions from food and agriculture. Non-food, 38.7 billion tons of CO2 equivalent, that is 74% of the global emissions. Land use, so 50% of the global habitable ice and desert-free land is used for agriculture here. So forest, urban area, shrubs, freshwater, and so on together are producing using 51 million square kilometers, 50% of the global habitable land. Agriculture is using a similar amount, and freshwater use always very high. So irrigation use is incredibly high. So you can see that the freshwater used by the agriculture is almost 70% in some countries like India, which are exploiting groundwater unsustainably. It's as high as 80 to maybe even 90%. Eutrophication, 70% of the global ocean and freshwater pollution. I will show more details of this a little bit later on. So agriculture is 8% of the source for global eutrophication. So all this nitrogen fertilizer use and soil, the way soil erosion happens in agricultural land because of tillage practices and so on, and livestock management, grazing practices and so on also contribute. So here, biodiversity loss, 94% of the mammal biomass excluding humans. Livestock is 94% of the global biomass excluding humans. So this is not directly nitrogen cycle, but nitrogen cycle is very much a part of driving this massive food and agricultural business. That's the main point we would want to make. And the analogy or metaphor for geoengineering is that when we do, let's say, sulfur dioxide or sulfuric acid spraying into the stratosphere, we talked about all the cascading unintended consequences like ozone hole, heating of the stratosphere, cirrus cloud impacts, coral impacts, crop yield impacts, ozone, etc., etc., right? So that's similar here. So we're just trying to understand how the intended production of ammonium as fertilizer has of course had unintended consequences of building bombs and killing people, but among all the good things it did in terms of feeding the population and maybe helping the population grow, it also has had these cascades, and the fossil fuel burning also has produced NOx, which have had other cascades through the nitrogen cycle as well.